All right, welcome. In this video, we're going to be calculating the energy released in a nuclear reaction, specifically the triple alpha process, where three alpha particles collide together to give us a carbon atom. The mass of each alpha particle is given here in unified atomic mass units. The mass of the carbon atom exactly 12, and one unified atomic mass unit is this many kilograms, 1.66 by 10 to the negative 27. So to calculate the energy released, we're going to be sort of leveraging Einstein's mass energy equivalence. First, we have to know what's the missing mass. And so we just need to sort of take three of these, and you'll just see kind of mathematically, if we multiply this by 3, we account for all 3 of the helium nuclei, we're going to get a number that's a little bit bigger than exactly 12, right? Because of this sort of fraction out here. So let's do that real quick in our calculator. You know what? Since I'm up here at the chalkboard, and it's like, chalkboard's kind of old school, right? I'm going to do a little bit of old school computation here. All right, so I'm going to times this by 3. I'm going to use the standard algorithm of multiplication up here on the chalkboard. You all get a calculator. I'll race you. Ready? Go. .004518 is what I'm getting. So if you times this by 3, you get 12.004518. Does that check out in your calculator? Awesome. 8 minus 0 is 8, 1 minus 0 is 1, 5 minus 0 is 5, 4 minus 0 is 4, 0 minus 0, 0 minus 0, 12 minus 12. So there is 0.004518 U extra mass in our helium nuclei than in our carbon. And so that must mean that when stars do this, they release energy. Okay, we kind of that's nice, one star's trash is another planet's treasure. So it's like the star's goal is to make the carbon, or it doesn't have a goal, but like that's what it's doing chemically. But as a byproduct of that, it makes heat and light, and it's like a good thing for us. We kind of like that stuff here. We don't just like the carbon for our carbon-based sort of backbone that all of our biochemical molecules are based on. We like the heat and the light, energy too. That's all good stuff for us, life forms here. So now we'll convert this to kilograms, multiplying it by this number, right? So if there's this many U unified atomic mass units, and this is the mass in kilograms of one unified atomic mass unit, then we just take this value and multiply it by this. All right, I think I'll just do this one mentally also, rather than like using the chalkboard and doing the standard algorithm of multiplication. I'm just going to sort of puzzle my way through this a little bit of mental math here. Let me see, 1.66 by 10 to the negative 27 times 0.004518. Let's see if I just hold those up in my brain for a bit. I think it should be something like 7.49988 by 10 to the negative 30, something like that. Maybe check that in the calculator, you guys. I don't know if I trust my mental math. Okay, so that's the missing mass. If you look at step 1, balance the nuclear reaction by ensuring the nucleon number and the proton number are conserved. So we did that. Because mass energy is conserved, the change in mass is equal to energy. So you calculate the change in mass. It must be in kilograms if we're going to record joules of energy. Okay, so using E equals mc squared now, we've got the mass. Multiply it by the speed of light squared. So we'll do this 7.49988 by 10 to the negative 30 kilograms times, we use the rounded value. So for these calculations, like we do this on Fridays for our quiz, you can use 300 million, or you could use since it's open note, you'll know that the speed of light is 299,792,458 meters per second. But if you don't feel like typing in all those, 9 digits, use a 3 by 10 to the 8. All right. So this would be 16, so that makes sense. So now on my calculator, I decided to use a calculator for this one. 6.7, we'll round that up to 5 by 10 to the negative 13 joules. Remember, you should be able to convert joules to electron volts. Okay, if it's a tiny number like this, then you could say a more sensible unit might be electron volts. So remember, that's where we divide by 1.6 by 10 to the negative 19 joules per electron volt. As an electron travels through a potential difference of 1 volt, it gains this energy. So we take this number, and I just keep the whole thing in my calculator, so it's a little bit more precise than this in my calculator. Divide by 1.6 by 10 to the negative 19. And I realize we've got an energy release of, let me write it out like this first. 4218682.5, and then clean it up by saying this is millions. Okay, so remember there's a prefix that stands for 10 to the 6 for this many zeros there. So I'm just going to call it 4.22 times 10 to the 6, right? So 1, 2, 3, 4, 5, 6. So if I thought about this in scientific notation, I'd say, well, that number is really 4.22 by 10 to the 6 electron volts. And the capital letter M, which means mega, million, okay, mega electron volts. So I feel like this is the cleanest way to report the answer. 4.22 mega electron volts. It's better than like this 10 to the negative 13 common, which is nice, right? Or this by 10 to the 6. So we should know that these metric prefixes, like what order of 10 they stand for, so we can turn this into that if we need to, or we can go sort of back the other way if we're reporting our answer a certain way. All right, this has been a calculation of the energy released in the triple alpha process. This is Dr. Schleich signing off. We'll see you next time.